Hello, everyone. Waiting for some more stragglers to come in. I'm also trying to be obsessive compulsive about my camera here. Supposed to be centered. Supposed to be parallel to these lines. This top is supposed to be right there. All right, now it's looking good. Looks like it's fairly centered too. Good deal. So, dang it, I always do that button. Anybody have any questions before we get cracking on all this? Actually, I should say, does anybody have any questions, period, because this is basically just a Q&A session anyway. So if anybody has any questions about a past material, now's the time to ask it. Then right after that, I'm going to cover chapter 39, at least the parts of it that I care that you know. Of course, I sent out an email last night, and then I sent out a follow-up email tonight or this morning. So hopefully you've got both of those. The last two tests are up. I apologize for how long that took. I did change all the due dates from 8/1 to 8/9. I think I actually changed them to 8/9 at, well, actually, I think I changed the test due dates to Monday at 11:59 a.m. So just before noon, instead of the 8/8 at 11:59 p.m., which is what I was going to change them to. But like I said, since I had a little delay on the tests and stuff, I thought I'd give you the extra 12 hours. Not that much, but it's still another 12 hours. Okay, yes, I do want to do that. Thank you. I'm glad you reminded me, because I was doing that earlier and completely got sidetracked. So I'm gonna go back there while you guys are here. I'm gonna go back to the modules and open that Respondus midterm. And I'm just going to open it so y'all can, again, test your Respondus, possibly have to upload or download the later upgrade to Respondus or anything like that that might be necessary. So the Respondus midterm, practice midterm, I'm on that now. And I want to edit it. And I am now making it open until August the 5th at 11:59 p.m. In other words, well after closing time. So the final exam, of course, is supposed to be on August 5th. And for this class, it's supposed to be on August 4th. My fault. So I actually gave you extra days. It's supposed to be on August 4th at 5:30 p.m. So I've definitely given it to you for long enough. So make sure you get your Respondus lockdown browser working and all that good stuff. There should be unlimited number of times you can take this. Let me double check, make sure there's no limits. Oh, allow attempts, allow multiple attempts. There you go. So now I've set it to allow multiple attempts, and I'm doing all of them. So you should be able to try it an infinity of times if you need, but of course you only need it once, because you're not really trying to take the test as much as you're just trying to make sure the Respondus part works. So does anybody have any questions on that? Thanks for reminding me, whoever that was that sent me that message. Oh, it was Austin Kelly. Yeah, thanks, Austin. So Charlotte asked, how many questions are there on the final? So I told the class earlier that it was between 10 and 20 probably, but they reminded me that the midterm, which I like, was like 25 questions. So I would say probably 10 to 25 questions is a more reasonable guess. If I decide to put a little bit more lengthy problems, they'll be closer to the 10 and 20 end as opposed to the 25 end. Because like I said, I want you to have plenty of questions to answer so that you can miss, even 2 and still get an A. But at the same time, I might want to to ask a couple of the more rigorous questions, and may obviously be worth more points than the less rigorous ones. So it might be a little bit less. If I find that when I finally make the final, if I find that the final exam is significantly different than that, in other words, it doesn't have 10 to 25 questions, or if it's really close to 10, like if it's 10, 11, 12, 13, or something like that, I'll let you guys know. Or if it's 30 or 40, I'll let you guys know as soon as I know. But other than that, I'm not going to give you probably any more details about it. I was just telling the students in the lecture this morning that I've in recent times and in the past, a long time ago, I've made final exams that were completely comprehensive. That's normally the scenario, but I need to let you understand that that means completely comprehensive. We just finished our finishing Physics 242. Completely comprehensive means including Physics 241. So, I can still ask you questions about, like, have an open response question and say, what is Newton's first law of motion? What is Newton's second law of motion? Or what is Newton's third law of motion? Or even Kepler's laws. Kepler's laws of motion were the first, second, and third. You should know each of those. Let me see what else. Of course, you guys did cover thermodynamics. So the zeroth law, the first law, and the second law of thermodynamics, and all the forms of the second law of thermodynamics are fair game. We covered relativity in my 241 class. So those of you who might have had 241 somewhere else, I would advise you to at least know these 5 things. And the 5 things are: 1, the principle of special relativity is that the laws of physics are the same for all inertial observers. You can see this in chapter 6 or 36, excuse me. The laws of physics are the same for all inertial observers. The principle of the constancy of light: the speed of light is a constant independent of the motion of the source and the motion of the observer. That's the other second principle of special relativity. So you should know those 2. You should know the length contraction formula and the time dilation formula, and the addition of velocities formula and how to use it. So you can look at a couple examples, or you can look at examples that I did online on my YouTube channel. That's really all I would ask you on relativity on a 242 course. I generally have relativity in the 242 semester myself, but here at TCC, they do it in the 241 semester. So that's why I do anything with it at all. So just be advised, other than that, everybody else, no matter where they were, probably covered all the chapters we did in 241. So just be prepared to know kinematics. And for instance, I might ask you a mass spectrometer question, and that's where basically you send an atom or a particle or a nucleus of an atom into a magnetic field. And because of its charged nature, it'll make an arc that's a part of a circle of certain radius. And therefore, since it's a circle, you need to know how to analyze that motion. And from Physics 241, that means you got to know F equals ma, which is Newton's second law of motion. You got to know that a is the centripetal acceleration, so v squared over r is that formula. So that's something you should know. Of course, you should also know your kinematic equations: x equals 1/2 at squared plus v0t plus x0. V squared is equal to v0 squared plus 2a parentheses x minus x0. For constant acceleration, acceleration is also equal to v1 plus v2 over 2. Stuff like that. So those are all equations you should know. Velocity equals dx dt. Acceleration equals dv dt. Or acceleration equals d2x over dt squared. Those are all things you're expected to know throughout this whole course, and you've probably seen it in the homework. So just be advised that could appear on the final exam. Be advised that basically I could make the final completely comprehensive like that, or I might make it where it just has some stuff from early in the semester, or I can make it where it just has stuff from late in the semester, or I could have it where it has a little bit of stuff from the first semester and then everything through the second semester. Sometimes I've taken, the last test or the last 2 tests and made that the final, maybe change the numbers or something like that. Sometimes I've, taken a couple of questions out of each test we had in the past and made that the final. So all those different things are possibilities. I just wanted to warn you so that you would, in studying, I don't think you should, if you've been doing your homework and doing your online tests well enough that you did well in the midterm, then you probably understood the material well enough that as far as reviewing for the final exam, the only thing you really need to do is look through the table of contents at the front of the book and look at all the stuff that should be covered. We didn't cover statics, we didn't cover fluid dynamics, but generally speaking, we covered all the way up through chapter 39, which we're finishing up tonight, and you watched the video on. And we did a little bit with, what was it, 43 elementary particles, or no, we did that in 241. I will not be doing any questions from elementary particles. I mean, nuclear physics is fair, so 41 might be a part of it. And by that, I mean, you know, if I give you atomic mass number and atomic number, you better know how to find out the number of neutrons in a nucleus. You better know how to find out the number of electrons if it's a neutral atom, or the number of electrons if it's a +1 atom or a -2 atom or whatever. So those are all fair game. But other than that, I'm not going to ask you any elementary particle questions in the final. I promise you that. Okay. So just make sure you look over that table of contents, maybe jot down some things, some fundamental equations, write out those various laws or principles, you know, the 0th law of thermodynamics, the 1st law of thermodynamics, the 2nd law of thermodynamics, Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, Kepler's first, second, and third laws. You know, you should know Maxwell's equations, obviously, because that was covered in this class. I will allow you on the final, I'll allow you 2 sheets of notebook paper, front and back. Okay, I don't think you need that many, but I will allow it. So those are all handwritten equations that are only the equations in the textbook that are labeled with numbers. In other words, you know, that says 41-1 or 22-3 or something like that. Those are all allowed. Plus, I gave you a couple special equations, like I rewrote Coulomb's law for an integral form where I had an r minus dr dq or r minus r dq, that sort of thing. And I had a similar type equation that I made special for the Biot-Savart law. Those are fair. You can write down those, but that's pretty much it. I would advise you to have a periodic table, even though I try to always give you the periodic table information you need in a given question, just in case I get so rushed that I didn't double check that. I would say have a copy of the periodic table. You're allowed to have a copy of the inside front and back covers of the textbook if you wanted to. So that includes some constants. That includes sizes like the radius of the Earth, the distance of the between the Earth and the Sun, the distance between the Earth and the Moon, the radius of the Moon, the mass of the Earth, the mass of the Moon, the mass of the Sun. All that is good things. So any of those you're allowed to have, and basically I don't mind you having any number of those copied. That also includes prefixes, SI prefixes. It includes tables of integrals. All that stuff's completely fair. I don't think you might need a table of integrals. You might need a table of derivatives, and you definitely need to know those constants. And like I said, I would want you to have a periodic table, so that's fair. I don't think you'll need a table of moments of inertia and specific heat and latent heat. You don't have to have those forms. I will give you those specifically. But like I said, periodic table, I might screw up. So make sure you have a copy of that. And the way the test goes in the respondus, you're going to show me your ID, your photo ID with your little face next to it. So I can say, oh yeah, that face matches that ID. You're going to show me the front and back of all the equations close enough that I can read it. So if you can see it on there and can read it, then I should be able to. And then you'll flip it over and show me the back. And then you do the other equation sheet that I'll allow you, flip it over to the back. And then you do all the sheets that are copied. So you can copy a bunch of different things and put them all on one sheet, and that'd be fine. That'd be a lot less crap for you to do. Or you can do it on 2 sides and show it to me that way. And remember, you got to show me your workspace. So just be prepared for that. So other than that, it's just going to be just like the midterm. And I did make you out the deal that if you do better on the final than you do on the midterm, then I will give you the final exam grade for your midterm and your final. So that means the final exam, which is now all of a sudden a higher score than you got on your midterm, will erase your midterm and be worth 45% of the course, because 20% is your midterm, 25 is your final. So now the final is going to be a full 25%. So I do want you guys to take it seriously. And I'm specifically partly giving you that warning about the, me being able to just take the last test or the last 2 tests or the next to last test and make that the final exam. That is something I could do. That's just me trying to get you to focus. Make sure you know that those last two tests are important. So don't just slough off on them. Just plan on doing it. I think I did put up a practice final exam. That's from a previous semester. That should be plenty good to practice. If it's not up there, I'm going to put it up there tonight. So all I'd really do to prepare for the test is, like I said, look over the table of contents of your textbook, jog your memory on some of those things, discuss those specific things that I just mentioned to you: Newton's laws, Kepler's laws, principle of relativities, those three equations from special relativity, kinematics, if you don't remember those, F equals ma and A equals v squared over r for centrifugal acceleration, that kind of stuff. So check those out. Other than that, I don't think you need to do anything else other than taking the practice test for the next to the last test, and the practice test for the last test, and the practice test for the final. All that is wonderful preparation for the final exam, and the more of it you do, the better off you'll be. So anybody have any other questions? All right, well, I'm going to go ahead and do the brief introduction to chapter 39 that I told you guys I wanted to do. So we're going to do this introduction to chapter 39, and it's not going to be nearly as detailed as as the chapter is. In some cases, it'll be more detailed because I'm giving you some details that are pretty interesting and pretty important. But in general, it's just going to be a lot lighter version. I think really all you're going to be tested on in my class is 39.1 through 39.5. So 39.1 through 39.5 is really the most important sections. That being said, I'd say you get a lot more out of life and a lot more out of your past chemistry courses if you read all of chapter 39 and chapter 40, because chapter 40 really brings it all home and tells you, oh, wow, that's why I did what I did in chemistry. They talk about covalent bonds and ionic bonds and how molecules are made and how quantum mechanics affects molecules. And like I said, it's just whichever one you take first, chemistry or physics, the second one gets all this credit because it's going to make you, it's just the second time you're seeing it, plus you're seeing it from a different perspective. So the one that comes in second is always going to seem like, wow, that was really helpful. So I like it when people have already had their chemistry course and they take physics and they think the physics is so awesome because it's explained all that. So anyways, definitely do that, guys. What we're talking about in chapter 39 is the quantum mechanics of atoms. So it turns out Schrodinger's equation, you can write that. And you can write that for an electron that's actually in the hydrogen atom. And all you have to do is put the electric potential to be the Coulomb potential for the actual nucleus. And in fact, you can do it like Bohr did. Remember Bohr, when he made up his Bohr model of the atom that turned out to be completely wrong, but gave us all these cool answers. And I've mentioned that it was sort of like God left us a little step stool to step up and see into the sink a little bit, not see everything that we needed, but see enough for us to think the right things. It got a lot of things right, even though it fundamentally was wrong. And you can actually do that with Schrodinger's equation. And you can even allow the fact that the individual electron orbiting the nucleus, and the nucleus can actually have more than one proton, but you can't have more than one electron. As long as you're doing that system, the hydrogen atom that Bohr did, or any atom that Bohr does with one electron, is actually right, meaning it gives you the right results for a one electron atom, no matter how many protons it gives you. Now, you can actually write an equation in Schrodinger's equation that way, where you actually treat it as if it's the center of mass of the system. So you end up having the reduced mass. In other words, the mass of the nucleus plus the mass of the electron. We treat the center of mass of the system, and then the distance is really the distance between the center of mass and the electron, the distance between the center of mass and the center of mass of the proton, and all that. And it turns out when we do that with the hydrogen atom, we get an exact solution to the Schrodinger equation. So it's really, really nice. And your book gives you those solutions. And there's some neat techniques of it, but it's really not hard. Differential equations in general is not that hard. It's just a prescriptive way of looking at everything, every equation you have, and trying to transform it into one of the ones we know how to solve. It turns out in this case, there, at least in the hydrogen atom case, there's a lot of ways to solve it. And there's a lot of different differential equations that exist already solved that have solutions like Hermite polynomials, Laguerre polynomials, Legendre polynomials, confluent hypergeometric equations, which are also called Kummers, Kummers. That's another one. Bessel functions, spherical harmonics, which is literally the harmonics of a sphere. If you imagine a balloon filled with water and you start beating it like a drum, all the different vibrational patterns you can get on the surface of that balloon, that makes a solution, if it was perfectly spherical, would make a solution called the spherical harmonics. And those differential equations are weird in that they only work for integer values of certain variables in it. And that's actually kind of neat because all those polynomials have been worked out in terms of those integers and stuff. And we're just like on the shelf from mathematicians studying math for no other reason than it's interesting. Because when we get the Schrodinger equation, we solve it, we look on that dusty shelf and say, oh, wow, there's a solution I can use. And you take that solution down and you use it and you're like, well, this is weird. This is telling me that I have to have some integer in, and that's one of the Laguerre polynomials. And then you look and he says, well, this one also has to have an L and an M sub L. And you're like, whoa. So you end up getting quantization out of it. And it's weird because the mathematicians had already come up with this quantization just because they were intellectually curious. So that's what we're going to talk about, and we're going to do. So the good news is that you don't have to solve these things. You don't have to know these differential equations. But I expect you, at least in a homework capacity as well as an example capacity, be able to take derivatives and integrals of these functions. I could possibly imagine a scenario in which you're going to have to solve like the infinite well or a finite well for quantum mechanics. And that includes, integrating to get the normalization condition for quantum mechanics. Those are things that I find reasonable for a final exam, even though it's from these last chapters. But let's say integrating the actual R solution for quantum mechanics for the hydrogen atom. No, I'm not going to make you do that on the final. Again, it might be something you can do on your homeworks. It can be something you can do on your own just to learn more about it. And I highly recommend that. But no, that's a little bit too much to ask a student on the final exam. So let's get started. So I'm going to turn my document cam on if I don't accidentally turn my computer camera off because I'm old and forget things and do stupid stuff. Well, it turns out that generally speaking, remember Schrodinger's equation is negative h bar squared over 2m. And the generalization of the second derivative with respect to x is really this del squared operator that we talked about before. And that would be, for instance, the second derivative of something that's going to be to the right of it, taken with respect to x, plus the second derivative of that thing taken with respect to y, and plus the second derivative of that thing taken with respect to z. So that thing is technically going to be the capital one if I do the right-hand side with the I h bar in it. So negative h bar squared del squared psi over 2m plus the potential times psi is equal to I h bar partial of psi with respect to t, where we understand psi, the capital letter, to be a function of r, theta, phi, and t for the hydrogen atom. Okay, it could be a function of x, y, z and t, but it turns out that's a nightmare and something you can't solve for the hydrogen atom if you keep it in Cartesian coordinates. So instead, we have to transform this del squared from the second partial with respect to x squared plus the second partial with respect to y squared plus the second partial with respect to z squared. We have to transform that into something with the spherical coordinate r, theta, and phi. Okay, that's really what has to be done to solve this. And I can't get this focused well enough. That looks a little better. Okay. So one of the techniques you'll learn in PDEs, which is partial differential equations, which most people don't get to take. I didn't get to take it. I've had to learn it all on my own from old textbooks and just physics books and stuff like that. Now, what we'll do, one of the main techniques you'll learn, since it's partial differential equations, that means it's equations of more than one variable. So, the function that you're solving for has at least, say, an x and a y, or x and a z, or r and a t, or a x and t. In the cases we were dealing with before, it was r and t. But in general, it can be r, theta, phi, t, x1, x2, x3, x4, any number of those. And of course, the technique that's most often used is called separation of variables. So you'd say, okay, let's hypothesize that this function of r, theta, phi, and t is going to be some f of r times some y of theta and phi times some phi of t. Okay. Well, it turns out this actually works. In other words, when you plug this in and you start doing these derivatives that are so nasty, you'll get basically the derivative with respect to r only acting on the f, and these two acting like constant functions. And the derivatives with respect to theta and phi are only acting on y, and so on and so forth. And it turns out that those functions are actually indexed by a number n, in the case of f of r, and a number yl m sub l in the case of this one. And in fact, the solution is actually a y function, and it's called the spherical harmonics. And then of course this one, phi of t, is there as well. So this turns out to be right. It turns out there's 3 quantum numbers that we really need to know. In fact, there's actually 4 quantum numbers that we end up knowing, but the solution that involves that 4th one really comes from the Dirac equation. It's a relativistic effect, and it's dealing with the angular momentum that the electron has. So it turns out when you do this, you actually get an equation. And if you want to know, for instance, what f of r is, f of r turns out to be the Laguerre polynomials. And they're somehow related to the Legendre polynomials. And we're talking polynomials, like, you know, you learned x squared plus 3x plus 4. That's the polynomial. And each power you go up, basically you end up getting a higher order polynomial. So the n equal 1 Laguerre polynomial might only have a r raised to the 0 power, and the n equal 2 might have an r raised to the 1 power, and the n equal 3 might have an r raised to the 2 power, or something like that. So these two are related. You don't need to know anything about them. I'm just giving you that information for your edification in case you're curious. It turns out the y sub l, m sub l, theta, and phi is called the spherical harmonics. Again, something you do not need to know, but if you look them up, you'll see that naturally comes these little integer numbers, L and M sub L, or even fractional numbers in some cases, L and M sub L and stuff like that. So that's the only reason I'm telling you it. So it turns out the psi of R, which is really what I called f of R a second ago, that ends up being 1 over the square root of pi r0 cubed times e to the negative r over r0, where r0 is also called a0, and it's 0.529 times 10 to the negative 10th meters, which is also called the Bohr radius. So this is another one of those examples where I'm telling you that it was as if, you know, God or the universe left a step stool for us to look over the edge of the counter into the sink. Because remember, I told you Bohr's model of the atom is completely wrong, but his calculation gave him exactly the right radius. This A0 that Bohr derived is exactly the one that this fancy equation with the right equation gives us. Not only that, it made him think in terms of waves, because when he reinterpreted his quantization of angular momentum, he figured out that that was exactly equivalent to saying that the circumference around the circumference of an orbit was equal to an integer multiple of the wavelength of the electron, which made everybody think, oh, well, maybe a wave equation is something important. And then, as I showed you, one way that Schrodinger may actually have come up with a wave equation, we don't know, I don't know that he did it this way, was by assuming that the solution psi would be some constant times e to the I kx minus omega t. And knowing that E is equal to HF or H bar omega allowed him to make a conservation of energy equation with this that actually gave him a wave equation. And then, of course, we get a wave equation, which is this guy, Schrodinger's equation, and we get solutions to it. So it turns out that really all we have left from the Bohr model of the atom that was actually right is the fact that there's certain distinct energy levels at which electrons can be, and you can't be anywhere but them. And the only way an electron can change from one of those levels to another is by either absorbing a photon whose energy happens to equal exactly the difference between the two levels, or emitting a photon whose energy is exactly equal to the difference of those two levels. So that's the part that Bohr got right, okay? His Bohr model was complete crap, but like I said, it was complete crap that happened to get a lot of stuff right. So that's kind of cool. All right, so this turns out to be, in fact, if I wanted to, I would subscript it with the proper quantum numbers and say this is the 1, 0, 0 wave function, which means n equals 1, L, the orbital quantum number equals 0, and m sub L, the magnetic quantum number, also equals 0. So that's what that 1, 0, 0 means. But you don't even need that for this part because you don't see the L, the N, or the m sub L in there anywhere. But it turns out that's right, okay? So when they go about doing these equations for the hydrogen atom, it turns out a bunch more quantum numbers come into play. And we already had the N quantum number from the Bohr model of the atom. And basically, we had a Z in there as well. Like I said, Bohr's model actually worked for any single electron atom. It can have any number of protons, but it just has to have exactly one electron. But one of the other things he got was that the energy, at least for the hydrogen atoms, E sub n, is equal to negative 13.6 electron volts over n squared, where n is equal to 1, 2, 3, ... That's called the principal quantum number. I'll abbreviate quantum number QN for some time. So these energies are actually right. The only thing is they're actually, it differs a little bit. There's some energy dependence that we later find out. Remember, we saw those evacuated glass tubes where they had sucked all the air out of it and then backfilled it with like hydrogen or helium or mercury or neon, right? And those things produce very distinct colors, little thin lines of a particular color, and then another thin line of another particular color, and another thin line of another particular color. Those things seem to be very crisp little lines. Well, when our technology got better, we could look at those lines, and sometimes those lines broke up into two separate lines. Sometimes they broke up into 3, sometimes they broke up into 5, and sometimes you could force them to do it just by running them through a non-uniform magnetic field. So that's where we ended up getting this magnetic quantum number m sub L. So it turns out when you do all this, you still have this wonderful formula for the energy, and you've introduced the idea of a quantum number. So the first quantum number is the principal quantum number. And as long as you're not talking about on a large scale, instead of, you know, really say the second, third, fourth decimal place, if you're not worried about the second or third or fourth decimal place, then you can pretty much say that the principal quantum number n is what the energy depends on, and that's all. Okay, and of course n has to be 1, 2, 3, ... And you'll see later how that has to do with electron configurations that you learned about in chemistry. The next quantum number is the orbital quantum number. So remember, we have now this planetary model of the atom where the nucleus is this itty bitty dot, and then the orbits can be in any plane, really, but the orbits of the electrons have a certain energy associated with them, and therefore a certain angular momentum associated with it. Well, that's what we're talking about here. And the orbital quantum number is actually given the symbol L. And the formula that you'll see in a second is from the actual equation for spherical harmonics. So you can do a Google search of differential equations, spherical harmonics, and you will see things like L times the square root of L plus 1. And that'll make some more sense to you. But L can only be 0, 1, 2, ... on up to n minus 1. In other words, if n is 1, it can only be 0. Okay, so ... forever. That's the way that quantum number works. And it really is a quantum number relating to the angular momentum, which remember we use the symbol L, and the magnitude of the angular momentum turns out to be the square root of L times parentheses L plus 1, close square root, close parentheses, times H bar. Okay. Now it's weird seeing that, but basically that tells you we can only have, like in the n equal 1 case, we only have L equals 0. So that'd be 0 times all this. It has 0 angular momentum. Okay. That sort of forces us into thinking about something along the lines of spherical symmetry. Because how do you have angular momentum being 0 when things are actually orbiting? Well, you could have it, but you'd have to have it like where one thing's angular momentum cancels out the other so that you can get 0. And the only way you can do that is really if it's spherically symmetric, at least in terms of my thinking. So the next quantum number actually is related to the same quantum number that we just did, but it's called the magnetic quantum number. And that one's called M lowercase l, n subscript l. And that has values of negative L plus 1, negative L plus 2, ... 0, ... L minus 2, L minus 1, L. Okay, so that's the values of it. And really what it is it turns out that L sub z, the z component of this angular momentum, is equal to m sub L times h bar. So this actually leads to something we call space quantization. But if you imagine this is your y-axis, and this is your x-axis technically coming out of the page, and this is your z-axis, then at least in cases like where n equals, let's say 2, where n equals 2, or where n equals 3, then L can go up to 2. And then that means negative L can go from negative 2 to positive 2. So if that's the case, you have one of them with L equals 0. And in that case, you have basically a y component that has a 0 size. So I'll write this vector as this, but you know the actual L, the actual magnitude of the angular momentum is 0, and you also know that since it's 0, the z component must be 0. So that's the ml equal to 0. So this is L for ml equal to 0 and for L equal to 0. But it turns out you can also get another one where this is L for ml equal to plus 1 and for L equal to, whatever it can be. And then there's another one for L where ml is equal to negative 1. And then there's another one where L is such that ml is equal to 2. And similarly, there's another one. Whoa, I drew too far. Sorry about that. L where ml is equal to negative 2. And all we mean by that is notice that up here, this would be 2 H bar. And this would be just H bar. And this would be negative H bar. And this would be negative 2 H bar. Okay, so that's what we mean by that. Now, the X and Y components are completely indeterminate. So they can be any X and Y components. Well, if you allow that to do what it wants to, then that means this thing's going to make a cone like this. And this one's going to make a cone like this. And this one's just going to make a flat disc like this. This one's going to make a cone like that. And this one's going to make a cone like that. And that's what they refer to as space quantization. It's an antique term that a lot of people don't use anymore, but it sometimes comes up, so everybody should sort of at least be somewhat familiar with it. Because the X and Y can be anything, you still have a discreteness, and that picks a point in space or a locus of points in space, i.e. this cone here or that cone there, locus of points in space that are allowed, and all the other parts of space are completely unallowed. So that's what we mean by space quantization. It's like there's something acceptable about this, but something unacceptable about the other ones. Okay, so that's space quantization. And that's our third quantum number. And like I said, it goes from negative L on up to through 0 up to positive L. And then our fourth quantum number is basically called the magnetic quantum number, which is the M sub L. Ooh, actually, I did that already. Yeah, excuse me. Our fourth quantum number is the spin quantum number. And it's kind of a weird one in that we use, well, it's weird like L was. Notice L, we had lowercase l, that's the quantum number, but it refers to capital L as something important. But the capital L is not a quantum number. Well, the same thing happens here. We have this quantity M sub s, that's the spin quantum number. And that M sub s can be plus 1/2 or minus 1/2. And that actually begets another quantum number. And this is the spin angular momentum. So just like we had an angular momentum L, we're going to have an angular momentum S for the electron alone. And that angular momentum is going to have a magnitude equal to S times parentheses S plus 1, close parentheses, close square root H bar. And for the electron, that S is always equal to just 1/2. Okay, but here's the kicker. The Z component of that angular momentum is given by MS times H bar, just like the LZ component was ML times H bar. So it's an exact parallel. Now, the reason they call this one the magnetic quantum number is they discovered that when you let a atom or a collection of atoms, say in a gas tube, when you subjected them to a magnetic field, you would look at those little crisp lines that I showed you in the spectra of atoms, and those little spectra lines would become maybe 1 or 2 lines next to each other. And it was the fact that they're really close to each other, and the fact that we couldn't tell them apart before, tells you that they're really only slightly different from the energy we get in terms of N. So in fact, it's called the fine structure. It actually is called the fine structure because what happens is you have a magnetic field that basically exists in space, and then the atom is going to be a little bit lower energy if the electron spin and the orbital spin line up in such a way that it reduces the total potential energy, not only due to the electron being attracted to the nucleus, but also due to the magnetic field affecting the angular momentum. Remember, we learned that when you have a moment of inertia, or excuse me, a magnetic moment, which is only required that you have a charge that's moving in a circle, then you have an angular momentum because it's moving in a circle. Therefore, the angular momentum and the magnetic moment are related. So there's a way in which you can have, say, the spin of the electron aligned with the spin of the orbit, or the angular momentum of the electron is lined up with the angular momentum of the orbit, and that might be a higher energy, whereas if they're oppositely directed, that might be a lower energy, but they're only going to be a difference by a little bit. So that's why it's called the fine structure. And later on, they actually discovered something called the hyperfine structure. And that's related again to another kind of interaction like this. So what we end up having is a total angular momentum, which we call J. And that total angular momentum is L plus S. And I was trying to look for that particular part just to sort of round out this part that we're talking about. And I am not seeing it now. Oh, there it is. Yeah, so when you talk about total angular momentum, that's actually in section 39.7. What it leads to is we get an angular momentum J for the atom itself is equal to the angular momentum for the orbit plus the angular momentum for the electron. And lo and behold, when we start messing around with that, we get a whole new set of quantum numbers and stuff like that, where the magnitude of this guy is actually J times J plus 1, close parentheses, close square root times H bar, and there's a M sub J again. And in fact, you can talk about a Z component and all that good stuff. So all those things come into play, and it's a whole, like I said, generalization to all this. And this is called the spectroscopic notation, is that stuff that you learn in the actual electron configuration stuff that you did in chemistry. So all of this is about angular momenta interacting with one another and angular momenta interacting with magnetic fields, and so on and so forth. So that's really the quantum numbers. And what I want you to understand from that is, because of these quantum numbers, which are literally indices in the actual differential equations that are being solved, and they have to be, because the solutions of those are only allowed for those particular indices. So what you get when you're talking about, let's say, the 1s2 electron, so this is for instance, helium. The electron configuration for helium is 1s2. The electron configuration for hydrogen is 1s1. And what this corresponds to is, this is your shell. This is your L, your angular momentum. So in this case, L equals 0. And we use a symbol S, which a lot of people think is for symmetry, but it's actually for another word, or spherical, because all of these S's are spherical, but it is actually for another word. So that's where these things come from. And you go up higher and you discover that there's also, you know, a 1s2, a 2s2. And in fact, the way you choose that is you say, okay, let's let our N's be right here. Let's let our L's be right here. Let's let our M sub L's be right here. And we'll let our M sub S's, if we really wanted to include them, we could put them right here. So when N equals 1, we could have, for instance, I'll say the configuration. We'd have 1s like that. That means N equals 1, S equals 0. M sub L, however, can only be negative L to L, so that's just 0. But then M sub S can be plus or minus 1/2. So the 1s shell allows you 2 electrons. And then the 2s is again N equal, in this case, 2. But then L is again equal to 0. And then M sub L again has to equal 0. Sorry, I should have wrote 0 instead of M. The problem with talking while you're writing, you sometimes actually write what you were getting ready to say. That's 0. So again, you get plus or minus 1/2, which means the 2s only allows 2 electrons as well. But when you go to do that configuration, what you can do is you can take this in and allow it to go n equal 1, 2, 3, 4, 5, 6. And then you can say, okay, well, L equal 0, L equal 1, L equal 2, L equal 3. Now, what we have is we write 1s here, and then right below it, because there's really only one choice, n equals 1 only allows L to be 0. So I can only put that there. And then I have for n equal 2, I have 2s, but the L being 2 allows, or excuse me, the n being 2 allows the L to be 0 and 1. So in this case, I've got a 0, but I've also got a L equal 2, so I can put 2p. And then for n equal 3, I got a 3s. And then, of course, the n being 3 means the L can be 0, 1, or 2. So I'll write 3p, and then I'll write 3d. And then I have 4s and 4p and 4d. But now, since n is 4, I can have L go from 0 to 3. So in fact, that is 4f. And they actually have letters they've chosen for higher orbits, but we really never need any higher than the f's. And then we write 5s, 5p, 5d, 5f, and 6s, 6p, 6d, and 6f. And obviously there's something here and there's something here and here for these, but we're not even showing those. Now, we can use this to do our electron configurations as follows. We can say, okay, I just have to go always from the top right to the bottom left at a 45-degree angle. That means first I do 1s, then I do 2s, then I do 2p, 3s, then I do 3p, 4s, then I do 3d, 4d, 5s. That's actually supposed to be a 5s that I hit there. And then 4d, 5p, 6s. So that's the order. Now we can write 1s. Let me switch to color other than blue. The blues are fine for the arrow. But we can have 1s, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s. And then after that, we have to go to 3d, and then 4p, and then 5s. And then after that, we go to 4d, and 5p, and 6s. So that's the order in which these shells and subshells come. So whenever you have n equal 1, that's a shell. N equal 2, these two make a shell. N equal 3, this one, and this one make a shell. But notice you don't fill 3s, 3p, and 3d until after you start filling 3s. So you fill 3s and 3p, and then you go to 4s. Then you go back to 3 and hit 3d. That's because the different orbitals are actually at higher energy, so you end up having a higher energy sometimes in a lower shell than you do in a higher shell. So the 3D shell has higher energy than the 4s shell, and these electrons are just trying to slip into the lowest energy gap you can get. So now that you have that, you understand how you can choose the order, and then you can understand, well, why do I know that it has X number of electrons? And that's what I'm showing you here with this table. So when I have 2s, I've done 2s. The next one is 2p. That's obviously n equals 2, which is also obviously L equals 1, which means m sub L can be 0, which gives a plus or minus 1/2. But m sub L can also be 1, which gives another plus or minus 1/2. And ML can also be -1. So maybe I should have put -1 first. But anyways, I'll say -1 and then I'll say +1. And this gives me another plus or minus 1/2. So you see, I get 6 electrons in P's. And then, of course, the next thing we get to is 3s. We've already covered that. So I'll say ... 3s, 3p, we've already covered a p. It's going to be exactly the same. It'll be 6 of them. 4s, we've already covered an s. That's exactly the same. But now we're up to 3d. So I'm going to say 3d. Well, that's n equals 3. And that's L equal, of course, 2. And that means that we can have M sub L equal to -2, -1, 0, 1, and 2. And each of those will have a plus, minus, plus, minus, plus, minus, plus, minus, and plus, minus. So you see that this one is 1, 2, 3, 4, 5 times 2 is 10 electrons. And of course, you can convince yourself that the next time we go up beyond a D is when we get to ultimately after 6s, we're going to run into 4f. So the next bit is 4f, and then 5d, and then 6p. And after 6p, of course, comes 7s. And so on and so forth. You're going down 1 and over 1 each time. Ideally, you draw this out so everything will be 45 degrees. I didn't draw it out, so everything was 45 degrees. So what you just want to remember is you're always going to go from the first one you come in on, you go down 1, over 1, down 1, over 1, and that's really what it is. It's called Model-Lung's rule. I think it's Modelung. That's an N, not a Model-Lung's rule. You go basically L goes down 1 and N goes down 1 in that order, basically. So once we have all that, now we can actually talk about, let's say, for instance, iron. Iron has, in this case, the number of protons, Z, the atomic number, is actually equal to 26. And I'm going to check my periodic table to make sure. Yes, it does have 26. So if we want to do the electron configuration for that, we're going to say, wait a second, here's 2. So I'm going down to here. There's 2 for that one. There's 2 for that one. There's 6 for that one. There's 2 for that one. So at this point, we're only up to 4. At this point, we're up to 10. At this point, we're up to 12. We get another 6 for this guy. So now we can say 18. And then we get another 2. That's 20. Another D is where we get in 10. So that's 30. So that's plenty far enough to get past 26. So I know my electron configuration for iron is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then, of course, at 4s2, we're at 20. That means we only need to take 6 of the 3Ds. So 3D is going to be 6. So that's the electron configuration for neutral hydrogen. So that's something you should be able to do. That means you got to know your quantum mechanics, the numbers and all that good stuff. I can ask you questions like what is the angular momentum for the 2s state? And you say, okay, well, wait a second, 2s is n equal 2, and s means L equals 0. So that means L equals 0. So L is 0 for that one. Or I could say, wait a second, what is the orbital angular momentum for the 3p state? And you say, okay, well, wait a second, that's n equal 3, but it's also p is equal to, or corresponds to L equal 1. So that's 1 times 1 plus 1, which would be 1 plus 1 is 2. So that's the square root of 2 h bar. And I could ask you, what is the z component of that? And then, of course, you just use the m sub L as well, which is the numbers over here. All right, so that's some of the stuff you have to be able to do. Now, that's not unlike examples 39.1 and 39.2. So these are like examples 39-1 and 39-2. So that's pretty fair estimate of what the problems that you need to know how to do are like. Now what I'm going to do is show you some of the neat solutions to the Schrodinger equation. So it turns out, remember the interpretation, the Born, what is it? The Born approximation of what the wave function is that psi star psi is a probability density. So that if you go integral from negative infinity to positive infinity, basically over all space, because this just suggests one variable. So in one variable, that'd be the integral of psi star psi dx from negative infinity to positive infinity. But in the more general case, it's psi star psi dv, where that's dx, dy, dz, or some other special one. That's all got to be equal to exactly 1. Okay. If you want to find out what the probability is of an electron being between r equals 0 and r equals 2 Bohr radii, then you integrate from 0 to 2r0, and so on and so forth. So that's what this is. And the star means complex conjugate, which you haven't really discussed yet. You probably remember a little bit about it from pre-calculus, but in here I'll actually get one chance to show you. So in the hydrogen atom, the wave function, we already talked about the first one. This is psi of r, and it's 1, 0, 0. So this is n equal 1, L equals 0, m sub L equals 0. That's equal to, in fact, 1 over the square root of pi r0 cubed times e to the negative r over r0. So what happened was they got this function, and then they had to do that normalization position right there. And when they integrated it from r equals 0 to infinity, using not just psi, but using psi star psi. This thing's completely real, by the way. So psi star is the same thing as psi. So basically they're integrating this times itself, which would be e to the negative 2r over r0. And they integrate that from 0 to infinity. But since they're using spherical coordinates, they'd actually have to say dv is equal to 4 pi r squared dr. When they integrated all of that, the answer came out to be 1 over pi r0 cubed. So they took the square root of that and multiplied it in front of this, so that when you multiplied them again, you'll end up getting pi over r0 cubed, whereas they got pi r0 cubed when they integrated it. I said that backwards a second ago. So this implies the integral from 0 to infinity of psi star psi 4 pi r squared dr equals pi r0 cubed. Okay, that's what that implies. Now, what we had to do is say, well, I needed a constant in front of this a and a constant in front of this a, which actually this a would become a star and this a would become a. So it'd be a star a has to be equal to the inverse of this, which would be 1 over pi r0 cubed. And when they did that, when you multiply, automatically the pi r0 cubed on top would cancel out with this one. So that's the normalization constant. And this quantity right here, psi star psi, times 4 pi r squared. That's actually something we call P of R. And that's really what is a more meaningful thing to graph, because when you graph that as a function of R, you can see what the probability distribution looks like for the wave function. And in fact, for this one, you get a function that looks like this. So that's R. This is P of R, which is really psi star psi times 4 pi R squared. Well, this probability density turns out to be a sharp curve upwards, and then it reaches a peak, and then it sort of gradually falls down. And this value, which basically, anybody know how you find out what R this occurs at? If you know the function that is this, how do you think you'd go about finding the R value that's right there?
Taking the derivative and set it equal to 0.
Exactly. So if you took the derivative of this, which you'll see as an example in your textbook, and set it equal to 0 and then solve for R, what you'll find is that occurs at R0, which is the Bohr radius. Okay. And then if you want to calculate the probability that the electron is between R equals 0 and R equal 2 times the Bohr radius, then you do the integral from 0 to 2R0 of psi star psi 4 pi R squared GR, and lo and behold, you get about 76%. And what that means is that if at any time, let's say we did 100 million checks of a hydrogen atom, and basically what we did is we forced the hydrogen atom to be forced through something that has a diameter of 4R0, and then we looked to see if the electron was in there, and we did it 100 million times. Well, that means 76 million of those had the electron come in with it, but the other 24 million did not include the electron, it just had the nucleus. So that's what that is. And you can see it's basically a spherical distribution, because it doesn't depend on theta or phi. And that's sort of the nature of it. It doesn't depend on theta and phi. In other words, when you start to use the L and the M sub L, which come from before, like I showed you here, the L and the M sub L came from the spherical harmonics. So when you start to include the spherical harmonics, that has to be not when L is 0 and when ML is 0, but when L is 1 or bigger. Then you start to get dependence on thetas and phis and stuff like that. So I will show you now that what the wave function looks like for the hydrogen atom for those other n values. So for instance, when I have psi, and this one, as you'll be able to tell, only depends on R. So I'm going to again say psi of R 2, 0, 0. That's still L equals 0 and ML equals 0. It's just N equal 2 instead of N equal 1. When I do that, that turns out to be 1 over 32 pi R0 cubed to the square root power. And, or see, yeah, it's the square root times 2 minus R over R0. And then that's times E to the negative R over 2R0, like that. Okay. So when you go to do P of R, notice there's no I's in here. So psi star psi is psi. Same thing here. Psi star psi equals psi times psi. Same thing here. So in this case, we're going to get 1 over 32 pi R0 cubed. I did write that as R cubed, right? Yes, 32 pi R cubed times 2 minus r over r0 squared times e to the negative r over r0, because when you multiply those two, it's 2 in the top, it's going to cancel out with the 2 in the bottom. I get all that. But now I also have, since it's p of r, it's times 4 pi r squared. So you can see this is ultimately going to be 4 is going to cancel out with a 32, leave an 8 in the bottom. So it'll be 1 over 8. The pi is going to cancel out, and it's going to be r squared over r0 cubed. I don't even need that 1 now because I've got an r on the numerator. And then times 2 minus r over r0 squared e to the negative r over r0. That's the p of r. And when you actually graph that, it looks like this. So let's say in this case, it goes up, reaches a maximum, then goes up, reaches a much higher maximum, and then goes down like this. This maximum turns out to be 5r0, and this maximum turns out to be just r0. So you see in the 2s state, you have some probability for the electron to be back at r0, which is the radius of the 1s state. But you also have a much higher probability. In fact, this is around, I'm going to say around 3.5, 3.25, and this is around 1. So that means you actually have about 3.5 times more likelihood of finding the electron at 5 times the Bohr radius than you do at 1 times the Bohr radius. So this is for the 2, 0, 0. But again, notice they didn't feel compelled to give you the theta and phi, but that's again because the L and the M sub L is 0, and the spherical harmonic function for L equals 0, M sub L equals 0 is trivial. It's like 1, okay? But if you take it a little further and get really crazy, then you can do, okay, let's look at psi 2, 1, 0. That's a little more complicated. And in fact, this one's weird, but it is actually taking into account the spherical harmonics. So it's going to be r theta and phi in reality is what that could be. And in fact, what it comes out to be is z. Now, remember, we were in spherical coordinates. All of a sudden, we're talking about z's. So that means z would be represented by cosine of phi. So I'll write that here. And it's actually z r times the cosine of phi, because phi in the spherical coordinate systems, you imagine a projection of the r vector. This would be the angle theta. This is the x-axis. This is the y-axis. This is the z-axis. And down this way is the angle phi. So, and this distance, of course, is the radius r. So if I took r and multiplied it by cosine theta, it would be this value right here, which is the z component. So that's why I'm saying z is equal to r cosine phi. And I just put that in there to let you see that, yeah, this is something that depends on the angle phi. But also it has the 32 pi, like we had run into before, only this time instead of r0 to the 3 power, it's r0 to the 5th power. And then it also has e to the negative r over 2r0, like that. And if you look at psi 210, or excuse me, 211, that again, I'll write it this way. That again is a function of r, theta, and phi, potentially. Okay. I don't like that, and I'm not going to let it stand. I'm going to erase it. Okay. That one turns out to be x plus iy. Now, x is, you can look at this and see that x should actually be r sine theta cosine, or excuse me, r sine phi cosine theta, and y would be r sine phi sine theta. So this includes the phi and the theta in here. And then this one will be over 64 pi r0 to the 5th to the square root. And then that's e to the negative r over 2r0. And then psi, remember when you have L equals 1, m sub L can equal -1, 0, and 1. So we just did the m sub L equal to 1. Now we can do m sub L equal to -1. Again, a function of r, theta, and phi. And in this case, it turns out to be just the complex conjugate of this one. It's x minus iy over square root 64 pi r0 to the 5th square root e to the negative r over 2r0. And when you actually graph those p's of r, if you will, in this first case, the L equals 0, I'll do it with this pen. So in this case, you end up getting basically a function that looks like this. You might remember it from chemistry. It's sort of like two balloons along the z-axis. X is here. Oh yeah, I should put y is here, not r, sorry. So this one you can see from this graph, it clearly has some phi dependence, because phi is only relevant from 0 down to whatever angle this is from here to here. And then again, nothing happens for phi being bigger than that angle until it gets down to this big angle, and then it becomes non-zero again up until it gets to 180. Remember, phi actually pegs out at 180, so you don't have to deal with that. But that's what psi 10 or 210 is. So this is psi squared for 210. Now these two, psi squared for 2, 1 plus or minus 1. Now that's a little bit different, but it's also something you'll probably still recognize. You have an x, you have a y, you have a z. Remember, when I multiply psi star times psi, making psi star is just turning that one into a negative, and making psi star for this one's turning that one into a positive. So literally you're just multiplying these two things together, and then you wouldn't have any more i's in it. And that's why we can graph psi star psi without having to refer to i's. But in this case, you're actually going to get a donut shape like that. And that's the probability density, if you will, for this particular state. And from that, if you just did it as a function of r, it would look again a little bit like the Planck distribution, even though it's entirely different units, are a little bit like the original s orbital for n equal 1. So it looks sort of like that, but the nature of it is because of its dependence on phi, it obviously has no dependence on theta, because theta can be any value. It can be, theta, remember, measures out from this way, counterclockwise, as seen from downward, looking downward along the z-axis, goes from 0 to 2 pi. All of those values are represented, but the phi has a very distinct allowed set of values such that it makes this little donut shape. So you got phi having some maximum value and phi having some minimum value. So this is clearly a function of phi, but that's because, like I said, x, let me write it in the red because the blue doesn't show up so well. X is equal to r sine phi cosine theta, and y is equal to r sine phi sine theta. So that's where the theta and phi's come into play. They just put it in terms of x and y, so you can sort of see it and think about it in the x, y, and z coordinate system without any worries. But notice once you take the complex conjugate of this one right here, you're getting x minus iy, and then you're multiplying it by x plus iy. That just gives you x squared plus y squared, which x squared plus y squared is just r sine phi, because it's this quantity right here. Any questions on that? All right, so that's the way this thing's working. This is the explanation of all the different shapes. Remember, we'll have a p sub x, a p sub y, and a p sub z. Notice this was all p sub z. But you can also have, when you have L equals, something higher, you can actually have a bulb that's here with 2 electrons in it, a bulb along the x-axis with another 2 electrons in it, and then a bulb along the y-axis with another 2 electrons in it. That's where you get the total of 6 electrons in the p orbital. So that's where all those diagrams came from. You can start to understand, for instance, the noble gases. The noble gases are ones whose outer shell or outer subshell is completely full. And because of that, it's spherically symmetric, which means it's not very attractive to other things. Ideally, if it's not spherically symmetric, then you'll have one spot in which if the electron's there, it'll be less attracted to the nucleus. So with the noble gases being in that last column on the periodic table, the spherical symmetry means that every electron at every position has an equal amount of pull on it from the nucleus. But if you have those bulbs, then that means this little electron out here up at this edge, that has very little pull on it from the nucleus, whereas maybe the ones towards the inner part have a lot of pull. So if something gets near that end, it could actually steal that electron, or it could actually pretend to share that electron, and that would actually make it something that's readily available for making chemical reactions with. So the noble gases have that outer filled shell or inner shell, and I say inner shell because it doesn't have to be, for instance, the D shell doesn't have to be full, just maybe the S shell. So maybe you're out on the 4th shell, and the 4th shell, which we saw earlier, went all the way up. Oh crap, I lost something. Hold on a second. All right. We saw earlier that the 4 shell went all the way up to F. So you could have, for instance, the D, you could have the F, you could have the S, you could have the P. All those different shells, subshells, are called subshells. And if that outer one is full, maybe it's not the D one, maybe it's not the S one, maybe it's not the F one, maybe it's the D one, or maybe it's the S one, or something like that. That could be spherical. But the main thing is it's also closer into the nucleus, so it's holding it very strongly, and therefore it's really hard to get them to combine with anything. So that's your noble gases. Then if you go to one level below that, in other words, that was 8 VIII, that was the column 8. But if you go to column 7, that's called the halogens, and they are actually 1 electron short. And they, of course, are not holding onto that electron very tight. And the orbital clouds can cross one another. And if they cross one another in terms of the waves, you can think of them as destructively interfering or constructively interfering. And when they destructively interfere, you get a downward well where they're overlapping. But if they're constructively interfering, you get a puckered well that's a little higher in the middle. So you have sort of a higher probability of the electron being between the 2 nuclei. And in fact, the destructive ones occur when the 2 electrons have the same spin. So like the 1 electron spin up and the other electron spin up, that makes the well in the middle. But when 1 electron's up and 1 electron's down, that makes a hump in the middle, specifically because of the Pauli exclusion principle. The Pauli exclusion principle says no 2 electrons can have the same quantum numbers. So when you've got the quantum numbers specified by N, L, and N sub L, then you had 2 different electrons you can have, plus 1/2 and minus 1/2. So if you're short 1 electron, you've only got either the plus 1 or the minus 1. And the other thing, the other chemical or element might be short an electron, so it only has 1 of them. If both of them have the plus 1/2, then they're going to constructively interfere and not work, because that would actually, according to the Heisenberg exclusion, the Pauli exclusion principle, that would force the 2 electrons to have exactly the same quantum number. So that's a no-no. But if one has a spin up and the other one has a spin down, then boom, they actually stick together, and one can automatically be orbiting the left nucleus and then go over and start orbiting the right nucleus, no problems. Okay, so that's some of the deeper meaning we get out of it. You can learn about the alkali metals. You can learn about the what do they call them? The earth, something others. I forgot what they were called. There's transition elements, rare earths, that sort of thing. All those different things have meanings from the ancient study of history, of chemistry, excuse me, not history, from the ancient study of chemistry. They all had meanings that meant something about their properties. And then now we can start to make sense of why they had those properties. Why did they have the principle or the property of being nobility, like untouchable, unwilling to mix with anything? And then why do we get covalent bonds versus ionic bonds and stuff like that? So that's all the stuff that's covered towards the 39.5 section of this chapter, as well as in chapter 40. The other thing that we did learn from this that I didn't mention when we got to it, but I think it's in 39.2 or 39.3, there's a selection rule that goes on that we didn't know about. Remember, Bohr just had the idea of a nucleus, and then he had certain allowed electron orbitals, and we could picture the electron transitioning from the n equal 3 to the n equal 1. And as long as it went from 1 to 3, the only thing that would be required for that is that the photon that happens to come near it has to have exactly the energy difference that is between E1 and E3. So if that photon has that energy difference, you set that energy difference to hc over lambda, you can find its wavelength, or you set it to hf, you can find its frequency. So if that happens to be the right energy, then spontaneously that photon disappears and the electron jumps up. And there was no rules about where it could jump up or where it could fall down. If it fell down, of course, it would spontaneously create a photon whose energy is equal to the energy difference between the levels. But we had no rules about, going from n equal 3 to n equal 1, or n equal 5 to n equal 2, or n equal 5 to n equal 1, any of that kind of stuff. Well, it turns out when you actually study this, there turns out to be a selection rule in which transitions are, I'm going to put it in quotation marks, air quotes, they're actually called, forbidden. Yeah, I lost a word there. Okay, so there's actually transitions that are forbidden, and I put the air quotes around it because it's not really forbidden, it's just really lowly probable. So if you have a scenario where an atom's not going to be disturbed very often, and it's going to sit there for a long time, then you might actually get that transition to occur because that transition has been given a long amount of time to happen. So if something's a probability of happening, once every 10 years, but you keep screwing around with it every day, you're never going to see that transition because you're changing it every day and restarting the clock. But if you have something that's going to be undisturbed for centuries, then you're going to see a bunch of those transitions. So if you ever see that particular transition of one of the forbidden transitions, then you know that must be somewhere that doesn't interact with stuff much and can do it for a long time. And you might conclude, for instance, that it's extremely low density gas. And therefore you say, oh, well, it must be the outer gaseous shell of a red giant. And that's actually where we sometimes see those forbidden transitions, is in the outer shells of a red giant. Okay, so that's a kind of neat sidebar. But that selection rule is delta L, the lowercase l, can only be plus or minus 1. It can't be 0. But it can go from L equal 1, which is a P, to an S, which is L equals 0, because that's a minus 1. Or it can go from S to P, because that's a plus 1. But it can't go from an S to an S, or a P to a P, or S to a P, or excuse me, or S to a D, or an S to a F, or any of that kind of stuff. So that's the actual rule we come up with, is delta L equals 0. Or excuse me, equals plus or minus 1. And that's the only, again, the only allowed transitions. Let me turn on the document cam so y'all can see that. So delta L equals plus or minus 1 is allowed transitions. Delta L not equal to plus or minus 1 are called forbidden. And remember, I put it in air quotes because in reality, you can't actually have the transition. It just takes a long period of time. It's just low probability. But all that came from the wonderfully exact solution of the hydrogen atom. Once you get to the hydrogen atom, things get really nasty. If we have a ton of computer time, we can actually compute the exact orbitals, not necessarily in a pretty solution way like these look, but we can still compute the exact right answers of anything we want to know. And when you get beyond helium, you can start to get even more complicated, or using even more complex computers, taking more time, or you could start to use techniques of approximation, which are perturbation theory and stuff like that. And that's normally what they do. And if you want to find someone who can do those calculations really well, you look in the chemistry department. Chemistry or even chemical engineering, they are the masters of using quantum mechanics to work on molecules as opposed to elements, or as opposed to atoms. So that's basically it. That's all I wanted you really to know. Again, I want you to read all of this chapter, and I would ideally like you to read chapter 40 as well, but I'm not requiring it. I'm just saying it would make you better off if you did. So the rest of the time, which is actually 45 minutes, right? So the rest of the time is all free question and answer session. If you don't have any, we'll just call it a day. But if you have any questions, I'll keep going until the last question is asked. Oh, I'll let you all know, by the way, I'm doing the same thing I did today at 10 a.m. and then again at 12:45. And if you would like to attend that, to maybe ask me some questions you didn't come up with tonight, then you just need to send me an email, or actually I prefer a text message, where you let me know your first and last name, what class you're in, the day class or the evening class, and tell me whether you'd rather attend the 10 a.m. or the 12:45 one, or both. That's okay too. And then I'll send you invitations so that you can attend them tomorrow. Otherwise, you won't see me again. You're just going to show up and take your final, and we're done. So the whole class is over. We finished all this stuff. All we've got left, and I want you to remember this, is 2 tests and a final exam. And I want you to try to take at least one attempt at both of those 2 tests before the final, because inevitably, I'm scared to death, some student is going to forget to do the test after the final, and they're going to end up getting 0. And that student might go from an A to an F, or an A to a C or something like that. And it's going to be really sad, but it's going to happen. So I want to make sure you guys don't do that. I gave you 5 attempts on these last 2 tests, so you can really do what you want to try to get a good grade. And the final is going to be difficult, but like I said, it could be difficult because it's only on the last test, or it's only on the last 2 tests, or it could be difficult because it includes stuff from 241, or it could be difficult because it's comprehensive. It could be difficult because there's one problem that's going to require you to do this really nasty integral. I could see that happening. For instance, the integrate the infinitely long line of positive charges to find the actual electric field at some distance r away from that, or integrate the Biot-Savart law to find the the magnetic field at a distance r from an infinitely long current carrying wire. Those are 2 very typical integral problems that I put on a final exam, so that they're not outside of the realm of possibility. I could also ask you to do those with Gauss's law and Ampere's law. I could also ask you to do cylinders with Gauss's law or Ampere's law. I could ask you to do a solenoid with Ampere's law, or a toroid with Ampere's law. Those are all fair game. Okay, so just keep that in mind. I could ask you to do the multi-step problem where you calculate the electric field within a toroid, and then you calculate the flux in that toroid, and then you use the flux and the current in that toroid to calculate the self-inductance, or the L, the Henrys, if you will, of that shape. And that's a very typical final exam problem as well, as I've been warning you the whole semester. So that's what it could be. Hopefully you guys will luck out. I'm going to try to make a test. My ideal test for this final exam would be one in which the average is about a 83 or 84, something like that, a good B, but not necessarily a high B, so that, virtually everybody does really well. Maybe a few people get a C because they really didn't understand it that well. Maybe some people get an A because they really did understand it very well. Hopefully nobody gets a D or an F. There might be, but hopefully not. So that's what I'm shooting for when I make this final. But if anybody doesn't have any questions, you're free to go. If you don't have any questions, but you might be curious about other people's questions, then hang out. But if nobody asks any questions, I'm going to go night-night too. I'm old. I'm going to bed at 7 o'clock. Not really. I'll probably stay up at least 2 hours. Anyone?
Well, I enjoyed the class, man. Appreciate it.
Thank you. I appreciate having you, Reggie. I'm sure you'll do fine, but
Thanks.
I hope all you make some really good grades. Remember, we got 20% of your grade coming from the lab, so you're going to do really well. You're going to do a lot better than you feel like you are now. I'm saying that to everybody, not just you, Reggie. Sorry.
I understand. But you guys, everyone, have a good one, and good luck as well in your endeavors.
Thanks, Reggie. Good luck on the final, everybody.
Thanks.
Nathan, do you have any questions, bud?
I'm just wondering, by chance, should we know how to solve like second order ordinary differential equations?
No. I showed you how to do that. Your job, I showed you how to do that specifically with the harmonic oscillator and the wave equations, the chapters on waves. But the reason I did that is so you now have a solution you're allowed to use.
All right. Thank you.
No problem. Have a good one, Nathan.